The next speaker is Brett Lyons, who I've known for a number of years now, when he was at the University of Michigan, right? I was going to say Michigan State as a joke, but I want to say that. So, or Ohio State, no. So I would like everyone's help in welcoming Brett Lyons from Boeing Company. Thank you.
Saying thank you again to Annie and our hosts, all the organizers and whatnot, and all of the attendees for taking their time to participate today. I brought to the conversation today an aerospace perspective on additive manufacturing. We have a lot of very specific requirements and opportunities that have allowed this industry to be a very good incubator for this technology. And as you'll see, where we are now and where we've been and where we're going is proof of that. So a little about myself. I work at Boeing Research. I'm in the composite processes group. Boeing brought me in to work on laser sintering. So I'm one of the second generation of employees that have been brought in to focus specifically on these technologies. I work on mostly laser sintering material development. We had a great introduction to laser sintering just a few slides ago, thankfully, so I don't have to do that as well. What I want to go over today, again, is that the requirements and the opportunities we have in aerospace are a good incubator and a good method for developing new manufacturing processes and materials in general. Additive manufacturing tends to be the one that we're really focusing on right now. You look at the composites industry, a lot of that came from a lot of the real hard work in the weeds development came from the aerospace industry. Vertical stabilizers in the 727 back in the 70s and whatnot. A lot of the composite cowboy work from the Navy and whatnot back in the day. All that work is a model for seeing how aerospace can work on these new materials and processes. So we'll go over just a few of the requirements. Obviously, each one of these topics you could really spend a lot of time speaking to. Then I'll show a little bit of where aerospace is today, both on our military side and our commercial sides. Within Boeing, obviously, the examples that I can best pull from. I'll show a little bit about what research we've done to drive additive manufacturing, so where we've pushed things through in the last 5 years or so, and then we can speak at the end about some of the challenges that we're looking at right now, particularly in new materials and laser sintering, although there are numerous. So with that, we can start with requirement and opportunity within aerospace and why they're important to additive manufacturing. So these airplanes fly over everyone's houses. Safety is just paramount and critical, and all of us within the company that I interact with, and certainly everyone that I'm sure I have yet to meet, takes it really very personally serious, at a personal level of seriousness. We have a lot of customers, a lot of regulatory bodies that dictate how we behave as engineers when you work in aerospace. You could list requirements from different governments, from airlines, from telecommunications companies for their satellites and whatnot, until you're blue in the face. But I think the subsection 25605 there from FAA is part of their Federal Aviation Administration's aviation regulations. Really kind of, from a material and process perspective for additive manufacturing, really kind of gives you the spirit of the regulatory environment that we're up against, and then the requirements to put new materials on aircraft. We have to understand in any given period of time that a given material is going to be installed on an aircraft, how it's going to perform, right? And that's it's easy to say as one quick sentence, but that means you have to know how the material behaves mechanically in all ranges of temperatures, humidities, with chemical exposure, at different vibrations, being exposed to different radiations, being exposed to pesticides. It's one of my favorite tests. In the case of fire, how do things behave? It's just a tremendous amount of information you have to develop, and you have to do that with a very high confidence level. So it's a tremendous amount of data that has to be generated before any one material can go on an aircraft. Even a washer for a side panel that gets sealed with a polymer, something minuscule that really doesn't affect the safety of the aircraft, has to be understood completely. That's the requirement that we work under within aerospace. And then to flip that to an opportunity, you can kind of take a customer perspective. So a number of airlines, particularly on the commercial side, are really sensitive to the aircraft weight. So you can look online a little bit. Boeing, obviously, we have a lot of information about aircraft weight and how that affects performance. I'm obviously not allowed to publish any of that. But what I can point to is some of our customers' work. So American Airlines is one of them, Alaska Airlines, Southwest, one, all have programs that are basically kind of employee initiative programs that allow their employees to make suggestions about weight reduction, about fuel burn reduction, et cetera, that really affect their bottom line. What those programs give us and what the public can see then is how sensitive these aircraft are to weight. So I don't need to read the slides here, but if we pull 1 pound of weight off one aircraft, within a year's time, that's saved 114 pounds of fuel burn. It's 1 pound. So that power brick you have, if you want to use an excuse, to go out and buy a nicer computer, just if you travel a lot, you can keep that in mind in your rationalization. If you take that 1 pound off that airplane, it's going to save a lot of pollution. Over the aircraft's lifetime, again, just that 1 pound offers quite a bit of fuel reduction. And then that also translates not only to pollution and just costs and everything like that, but also the bottom line of the airlines. The revenue numbers you'll see associated with airlines are huge. They circulate lots and lots of money. These materials, these airplanes, and everything are really, really expensive. But the profit margins are really slim in airlines. It's really hard to make a lot of money on that. And these kind of numbers are things that they care about. So when we talk about that we have opportunity to reduce weight that actually has a real significant impact on society. It's an environmental impact, it's a cost impact, it's a commercial impact for us as a company selling airplanes and whatnot. And we're always looking for ways we can do that. Boeing's pretty, again, that bottom line drives us pretty hard. So we're always interested in technologies that might get us there. And additive manufacturing is one of them. I'll speak to it, reasons why in a little more detail in a second. So going back to the requirements, this is just a little bit more of a bulletized list of the type of things we have to look at for a polymer, and we have to understand completely, again, with a very high level of confidence before we can put it onto any aircraft. So you can see is full range mechanical testing, temperature, smoke release toxicity. In the very unfortunate and thankfully very, very rare event that there ever is any kind of fire on an aircraft, rest assured the polymers that are around you are really, really hard to burn. The new ones and the base, driven by the FAA's requirements and whatnot, are very, very resistant to fire. You can see some really extreme examples here of flammability tests on the bottom right. I mean, these are polymers. These are materials that start out basically as fuel, and we get them to behave like that under really extreme thermal conditions. It's pretty amazing chemistry, and then the processing that goes along with that is also equally important. So again, some of the detailed type stuff. If you're not familiar with working in that type of requirement, these are the tests that we have to look at. Just some of the tests we have to look at for any given material. So why we think additive manufacturing and why we've shown additive manufacturing can really impact the weight and overall performance of our aircraft. So we had general instruction, like part count reduction is a huge thing. Obviously, flow time is cost and whatnot. Flow time for manufacturing is a lot of cost, and that's something to consider. But there are also other benefits in the aerospace world that we also tend to think of. One of them, I try to think this is kind of a digital to physical loop. So with additive manufacturing and then the inverse technology, reverse engineering technology, laser scanners and things like that, we're able to flip and flop between physical space and digital space very, very easily with a low enough cost and low enough time such that it's and enough accuracy such that it really is a viable tool for engineers. So we can make a part, we can make this chair, we can laser scan it, we can take it into the digital space. Now we can do FEA on it, we can do flow analysis on it, we can, whatever you want, whatever types of computational processing you want to do, put on that. And now with additive manufacturing, we can take that newly generated data and easily spit it back out. And when you start getting into the real strict performance requirements for an aircraft part, those optimized designs are really, really important. So that's one of the real enabling technologies why we're interested in additive manufacturing. Second is the manufacturing flexibility. Again, we've had a great introduction to this just a little bit before. But basically with additive manufacturing, we're dealing with a batch process. So we can make first batch of parts faster than any tool maker can even set up the jigs for us on a CNC machine to cut his mold and whatnot. But at some point, our batch process is going to be that much more expensive such that you're going to reach a cutoff point in terms of quantity where a molded process or a tooled process and maybe even more assembly process will eventually be cheaper in most parts. Every part is its own example that you have to consider details on. But at that point, then you can transition over to your kind of more standard, robust manufacturing if you ever get to those quantities. Now in aerospace, when we're making even the highest rate plane that we're, both Boeing and Airbus are making right now is in the range of about 40 units a month. So if you have one unique part on that, that's 40 parts a month or so is one of your highest quantity requirements that you'll see. There are a lot of commodity parts that might have much higher, especially like fastener, that have much higher quantities than that. But when you're talking about 40 a month to an injection molder, that's not even, it's barely getting the tool warm. It's really, you can kick out, 40 parts an hour easy. So that's an important thing to keep in mind is our quantities are appropriate for additive manufacturing. And the last thing is we've got robust processes now. So what I'm going to focus on for the rest of the talk is selective laser sintering. It's kind of the Cadillac of additive manufacturing processes. The powder-based processes allow unsupported geometry, so you can do really the kind of complex shapes that we need. It has, we're working with semicrystalline thermoplastics, things like nylons. We'll speak to the polyaryls, polyphenylene sulfides, stuff like that. These are robust materials that we already use in the aircraft, and this is the process by which we can form them into the shapes we need. So we have viable processes, that manufacturing flexibility, and then also the downstream type things. Those are some of the examples of why Boeing has invested in additive manufacturing, why we incorporate it into our aircraft. Speaking of incorporating an aircraft, we don't talk about it too openly, but it's been disclosed for a number of years. So this is all publicly released and whatnot. Since 2002, Boeing has been putting a fair number of parts on our tactical fighter aircraft in production. So it's not just a prototype, it's not just a one-off demonstrator or anything like that. This is mainline in production. You walk into the factory, guys on the floor are putting parts in, as you can see right down there on the bottom. They are installing these parts on the aircraft, and we have been doing so since 2002 in serial production. We don't talk about specific programs, we don't talk about specific numbers and whatnot, but needless to say, it's a fair amount of parts that we've been flying for a long time, almost a decade now. The interesting things about that, so we used additive manufacturing at that point and investigated it because of geometry constraints. We had a new aircraft, very tight constraints. We didn't have the ability to manufacture the ductwork and the brackets and whatnot with traditional means that would allow us to actually fit everything we need to into the aircraft fuselage. So we had to use some kind of process that could do these really crazy squiggly parts. So that was, the big driver. Obviously, all the other benefits were taken advantage of, no tooling costs, et cetera, et cetera. The other interesting thing about these programs is, in this particular aircraft type, we keep very good relationships, obviously, with our government customer in this case, and we also visit depots quite a bit, maintenance depots, whatnot. So since 2002, on this program, for the, let's say, over 100 parts that are on a given aircraft, we've never received or heard of one reported failure of these parts. So they're a little bit of that. Well, that tells me as an engineer is they're probably a little too heavy then, especially the use condition that they're put in. But that's impressive, right? So we had a question about mechanical properties. We have to understand that. We do understand these mechanical properties in sufficient depth to be able to engineer these type of components. Now, you look at these. Oh, these are just air ducts. This is what I get from my structures people in Boeing. I think, oh, you guys are just making air ducts and widgets and whatnot. Well, that's true, but anything you put on a fighter aircraft is even if it's just sitting there bolted to the wall with a do not step sign or something like that, is experiencing the G loads, the temperatures, the vibration, everything that aircraft sees. That's the equivalent of grabbing a piece and pounding it against the wall time and time and time and time again every day for decades, well, almost a decade in this case. And we can talk about strengths of given materials. We can talk about all the testing we've had to do to understand that and whatnot. But keep in mind the image that you see here on the left side. Keep in mind what these requirements are like. And instead of talking and putting up graphs about mean time to failure and fatigue strengths and stuff like that, I figured I'd just show you what the environment is like that these parts are living in. That's what they do every day for 10 years. This is kind of a general video. You'll see some of the applicable aircraft and programs, but needless to say, these are real working environments, very challenging. They're all over the world. Literally, they're seeing, extreme sun radiation. They're seeing freezing cold temperatures, everything. Lots of load. The people that are operating with them, yes, sorry, kind of a general video. People that are operating these parts don't have any particular love for this technology. They're not babying these parts at all. They don't know them from any other part that's on the aircraft, functioning at this level. And that to me, when I came into Boeing, was a fantastic surprise to see that this level of engineering had been accomplished with additive manufacturing. So, I mean, the just landing loads alone, you're looking like 5-6 Gs slamming down carrier decks and whatnot. I mean, try to do that with your hand. Like, that's really, you have to really hate that part to give it that much of a load yourself. So that's where Boeing's been. That's where Boeing was when I came into the company. And what I've worked towards, and what my colleagues also what we collaborate on, is transitioning that into the commercial sphere. So there's a lot of technologies start in the military applications and whatnot for numerous societal reasons. You can even get into psychology with that. They're thankfully now transitioning into the commercial aircraft, which are much more viable economically, right? I mean, fighter aircraft are produced in really small numbers. Like it's a niche product. It's a very special product, very expensive. Commercial aircraft are approaching, with the production rates that we're forecasting, are really approaching almost a commodity item. We're going to get 40 a month for a given component is getting, or for a given aircraft is getting there. So we've been working to transition this from, again, the commercial aircraft or military aircraft onto the commercial side. One of the big things that's been amazing for me to see is that once we published specifications within Boeing for the materials and the processes we're using to make these parts, the engineering community has just allowed that to grow, or facilitated those processes growth organically within the company. We started with 787, and let's just say almost all of our other commercial aircraft, independently of any pushing on a technologist perspective like mine, have all adopted these technologies where they're applicable. Each one of them does their own trade studies, economically, mechanically, and in terms of engineering and whatnot. So that's the best validation, I think, that from an aerospace company we can give to additive manufacturing. All these independent design engineers are making these decisions, running these trades on their own to put these parts on the plane. So a few notes on research. So that's basically where Boeing's been, where aerospace has been, and now looking forward. Here's some examples of kind of mature technologies that we've developed and we look at that are specific to additive manufacturing, kind of related to that digital physical loop. So one thing is the thermal control of additive manufacturing machines is critical. I'll be glad to bore anyone to tears about that tonight over dinner if you want to. But needless to say, it's a really difficult problem to control temperatures spatially in machines that are as dynamic as additive manufacturing machines are. You've got lasers tracing around, you have different material feed sources and whatnot. To do that, it's taken a lot of effort. You can see we've gone into thermography, in-process thermography. The challenges involved with additive manufacturing have really pushed us to look at process control, I think more so than most other established processes, just because of the needs for consistency and whatnot. Inspection, so we've really, this is one of my personal favorites, really gotten into microcomputed tomography. So we're making all these really crazy, shapes and whatnot, but how do we actually inspect them? How do we actually know what we have in full 3D? We do planar cross-sections with microscopes. That's nice, but you're starting to destroy your sample, at the level that we're really interested in investigating. Whereas micro-CT really offers a unique perspective to start visualizing on very, very fine scales and even larger scales the geometries that we're able to create. So a few notes on current problems. So we had to mention before of need for new materials. So for a host of reasons, mostly temperature performance and flammability performance, we need new thermoplastics to operate robustly in laser sintering. This is what I live at Boeing. And so in general, the industry, particularly laser sintering, is familiar with nylons, polyamides, particularly nylons 11s and 12s. Now we look at these new material families, polyaryls, peaks, PEX, things like that, polyphenylene sulfides, polyphthaliamides, things like that. And they behave totally differently in this one process. And all the information, all the literature that we have, which is not very deep, it's only 10 years deep or so, is based on these material families. And then when you take this other material, which behaves just completely differently, and you put it in the same context, you're kind of almost starting from scratch in a lot of ways. A few comparisons. It'd take a long time to belabor some of the points, and that's what I spent a lot of space in the paper doing. You look at the difference between the materials. I mean, you look at the melt temperatures and then the specific heats of the material. Not only do you have to go higher, it takes a lot more energy to get them there, and then how much energy does it take to transition them into a melt regime and whatnot. When you start really looking at these different material properties, again, which is each one of these is a whole thesis just comparing that set of numbers right there. In the context of laser sintering, it illustrates the effort we have to put forward to bring these new materials into use. Thankfully, you can see parts in the bottom, and that's where the proof is right down there in the pudding. So we are able to make traction on these, and we are bringing new materials that are much higher strength, much higher capability into additive manufacturing. Again, just to further that contrast, you can see a layer being scanned right there in the machine of these little airfoil sections and whatnot. It's a highly dynamic environment. I can't say that enough. And then, again, looking at where the polymer industry is usually dealing with and thinking about processes like injection molding and autoclave processing, kind of net whole part material energy input at one time type processes, whereas additive manufacturing is infinitely discretized and quite variable. So whereas injection molding, you get to heat up, with some control, apply pressure when you're molding your part and whatnot, and then let it cool down basically as fast or as slow as you want to, because you're dealing in a controlled space with takes some engineering effort to do that. You compare that to additive manufacturing. We bring these materials up really close to the melt, and at some point, for every given little discretized part on the component, you're then running it through a different thermal cycle, right? So how do you control that? That's really, really challenging. We hold these materials right up to their melt point, right? Laser passes over it right away, brings it into the melt regime, and then it starts cooling down, and then we hold it basically where all the other powder around all the other powder around it is staying as well. It's a really really horrible thing to do to a polymer, and you have to have very specific tuned polymers to actually work viably in these processes. So again, this is a lot of stuff. Hopefully in the next few days we will be able to get into the weeds to this degree if anyone's interested. But that's an illustration of where we are right now, what we're looking at when I go back to work on Thursday. Anyway, so moving forward, kind of summary, we have new materials coming online, and I focus on polymers, so that's what I'm able to speak to. Metals are moving forward as well. Metal parts, if we put titanium on a plane, it means it's carrying load. It's the only time we ever put a heavy material like that on an aircraft. So the risk associated with it is that much higher. So we've had to have a certain level of understanding and confidence with the polymers just to make air duct widgets, washers, things like that. When you start putting titanium parts on an airplane, you better understand how that material is going to behave. And that thankfully FAA and those type of bodies enforce those type of regulations. So it's a much steeper development curve to follow. So those new materials are going to obviously extend into new applications. There's going to be organic growth in terms of number of parts, size of machines, which is just kind of cart before a horse. The number of applications are going to drive the machine technology, et cetera, et cetera, et cetera. But there is a natural progression that we're already seeing just within Boeing and our supply chain. One thing that we have noticed is there's talk of patents. From a technologist perspective within additive manufacturing, I have to say it's been a good education for me to see our patent system work in that context. I'd say, and I think most people familiar with the technologies would agree, that the way in which additive manufacturing companies, just by their nature and the type of technologies that they're using, have used the patent system is almost really abusive. We're really, frankly, it's embarrassing. We should be 5 years ahead of where we are now, to be honest. But again, the level of complexity that we're dealing with and the subtlety you have to understand when you really consider what's new and what's inventive in additive manufacturing is typically beyond that which patent examiners have the time or the expertise to consider, and that's led to a lot of problems. So that's a maybe not very popular perspective to have on patents and intellectual property, but definitely it seems to be the case in this industry. So we've had a great demonstration of how these technologies are important within countries like the United States that pay labor enough to actually have a living wage and whatnot. These technologies are going to be quite competitive with it, and why? It's because they're faster than boats, I think, is a lot of what comes down to in the near term. So in a number of industries, you have, if you're going to deal with low-cost manufacturing and whatnot, you have to also burden your shipping time in that as well. We make parts in a day or two. Right? The boats, you're not getting through customs in a day. So it's kind of another interesting thing from Boeing's perspective, particularly when you get into situations what we call AOG, aircraft on ground. We have $300 million airplanes. If they run into a landing strip light or something like that, they need that airplane fixed because that aircraft is a very valuable resource. They pay a lot of money to get that going. It's the same with like oil and gas industry. Individual parts can have just grossly exaggerated value by their place in the system, right? If the system's broken, you have to get a widget on that aircraft really quickly, and additive manufacturing is going to allow you to do that. You're not going to be able to even get a part made and put on an airplane before you can make one at a closer facility. So that's something that Boeing keeps in mind as well. Machines are becoming more robust. So there's lots of inline process control and whatnot. It's really getting complicated. But it's fascinating as well, and thankfully there's a lot of progress going that way. Inline, basically thermographic control is one of the next ones that's going to start coming out. You can see that in patent literature already. So we have infrared cameras controlling the heat input on the machine real time with a laser scanning over. It's just like, if you're a nerd, it's exciting. And lastly, the analytical methods really need to mature as well. So when I bring a design like that, I had this experience myself to a stress analysis, and I showed him a picture of that, and he just laughed. He said, "Really, Brett? Like, I'm not even going to look at that structure in terms of analyzing it for how how it would actually perform, in a given situation. And then I brought him the physical part, and it was helpful in that obviously having that kind of prototype was very valuable for him to be able to start thinking about it and feeling the part and whatnot. But the reality is the analytical tools we have available that are robust enough that don't require a grad student's whole semester to complete the analysis with are not really able to easily handle these kind of geometries, nor do we understand really what we're making here. And that's where that kind of micro CT stuff starts coming into play and whatnot. We've thankfully outstripped the designer's ability to really know what they're drawing. So there aren't any more excuses for them from the manufacturing perspective, but we have to move those tools along as well. So I hope that was a reasonable kind of summary and overview of how aerospace thinks about additive manufacturing. Again, went over the requirements that we operate in, the opportunities for weight reduction, and how valuable that is for additive and doing complicated parts. Showed a few examples of where Boeing in particular uses this. Obviously, our competitors are starting to use it as well in their products. So it's growing just beyond our company, thankfully, to help bolster the industry. A few examples of the kind of research we've had to do to really advance the process a little bit in order to meet these requirements to keep the airplanes safely above your head and not on it. And then some of the areas we're working with new polyaerials and new materials for laser sintering and whatnot. So I hope that was a reasonable overview. And I guess with that, we have time for questions.
Any questions?
Hi, Madhu Iyengar, IBM. Can you comment on the use of alloys and whatever metallurgical constraints that might come with it in additive manufacturing?
For metals. Yeah, metals isn't my area of expertise, but I am related to it, close to it and do see it. So you have specific issues with metals. With aerospace, we mostly are interested in things like titaniums and then the light metals, like aluminums and whatnot. Aluminums and the light metals tend to be really, really, really conductive. So control of the part and the part geometry is exponentially more challenging. So you've got a really high melt temp. You can't preheat like we do in laser sintering to give a more isothermal condition, right? So your temperature gradient in terms of time and space is massive, and now your conductivity is really high too. So it's very challenging that way for those materials. For the titaniums and whatnot, you get into notch sensitivity issues. So all right, so now we can make this wonderful part, has this nice shape and whatnot, and now it has this rough surface which knocks our properties down just tremendously. So how do you deal with the surface on that? So you can do quite a bit of work, with your particle size distributions, your layer thicknesses, energy input gradients, and stuff like that to get the feature size and the layer size smaller and smaller and smaller. But that's still kind of a challenge and a problem. With titanium in particular, now you start getting finer and finer and finer particles. When your lab explodes. It's kind of an issue that way as well. So that's kind of where metals are now. The engine companies, as mentioned previously, have really focused a lot more on that. Because when we have a metal part, most of them are big forgings. That's you look at 787, and most of the metal there is large forgings that are machined and whatnot. That's where it's buying its place onto the aircraft compared to carbon fiber. So additive manufacturing is still, the biggest parts you can make in metals are like yay bigger. So heat treat is another huge thing with that too, actually keeping the geometry stable.
Hi, Kathy Weed from Eastman Kodak. Nice talk. I was curious, you actually hit on this in your answer to the previous question, but you said you were making air ducts. I was wondering if surface finish was an issue and if there's anything that you do to mitigate that.
Right. I do work on that. And it really comes down to finding automated processes to do it. And we develop processes to look at the surface finish of polymer ducts. And thankfully, there's a lot of background technology in like the Deber Industries and whatnot that we are working with on that. But the best example I can give to that is the surface finish, particularly on laser sintered parts as we process them, is consistent enough to be able to work predictively. The example that I was given when I came in was on one of these tactical fighters that I showed. Simulations on a test, not simulations, tests on a stand before we load these new ducting systems in the aircraft. And basically, they have a predictive model in terms of how much flow they're going to get at these given points and whatnot, and then they measure the actual result. And we were within basically the test margin of error for the first laser sintered assemblies of ducts that we put on the aircraft. Whereas typically, when they're doing multi-part assembly and they have all these cuffs that are joined and hand bond and whatnot, they're lucky to get within 15–20%. So they margin, they oversize everything, make everything heavier because of that. So it's consistent enough to be able to work with, but we do work on it to improve it. It's actually more important for appearance in the commercial aircraft, that's really where we care about surface finishes, making sure we can get parts to the customer. We have different regulations about if the customer can see it during landing and takeoff, they can have a certain appearance. If it's visible all the time, it's another appearance. That's what's really driving it is fashion. So.
Hi, Brent. Great question. John Zhang from UT Austin. I have a really basic question. I probably missed this. So in terms of the airplane, right? So what's the percentage of the parts made using this AM process?
Percentage?
And what's the percentage in terms of the cost?
The overall percentage is really small, especially if we start considering, I mean, there are millions and millions of parts in an aircraft, and we're putting a few hundred or so on. So that gives you kind of the ballpark. And then each program's different. Each one's going to have different numbers of parts and quantities and whatnot. The cost for the aircraft, again, also is thankfully infinitesimally small compared to what we pay for, the rest of the structures of the plane. The comparative cost, I think, maybe is more to the point. The comparative cost between an additive manufactured part and a molded part is also quite different. So we'll pay easily hundreds, maybe thousands of dollars for a simple part with all the quality control we put onto it and whatnot. That's typical and doesn't bother us at all, because the mold, to cut that mold to make that part via rotomolding or composite layup or whatnot is a $50,000 mold. So you look at you can do those trades, and your tooling costs, and then all the tool storage costs, the tool maintenance costs, all the added assembly you have for these different components, all the sealing you have to do, all the finishing on these molded parts easily gives additive manufacturing typically a cost benefit, quite a bit of a cost benefit, comparatively speaking.
This is RC from Eastman Chemicals. You hinted about thermography. Where is the state of art on controlling the spatial temperature profiles?
It's so thankfully this isn't the most leading work isn't at Boeing, so I can speak about it a little more freely, thankfully. So if you look at patent literature right now, there's EOS GmbH, that's a German company, and they have patents in on this. So Boeing also has patents on thermal control of the machines. But basically, we can mount cameras within the chamber. And there's already existing software that actually came from the aerospace industry for sensor reasons and whatnot, to be able to basically define zones, and then you can take that output as you can translate that into a given voltage for a heater that is known to control that area of the part bed and whatnot. So that's kind of that's the state of where they are. They're prototype machines that have that in development, but nothing's saleable yet.
Hi, Brett. Kevin Schlichting from Bryant Whitney. So you had some parts that you showed that were deployed. Have you used material models and process models to optimize the design on those parts?
Well, yeah, quite a bit. So the first generations of parts were designed in a much more standard, a very standard approach, and we're just kind of swapping in geometry that they knew they could do. On 8.7 and the commercial aircraft that we're moving forward with, we're doing quite a bit of, particularly in the ducting flow simulation. And we do a lot of internal geometry to really control that flow in the way that we want to. So it's, as far as the process tools that they use to design that, I don't think they're really any different than they would be for any other part that they'd make via another process. But the geometry that we're allowing them to make is what's differentiating. So I mean, we use standard, BCFD and stuff like that for those designs. I'm pretty sure. Did that answer the question?
Rahul Sarpeshkar, MIT. You had this interesting graph where if you plot time and cost versus quantity of parts, for small quantities, additive manufacturing is good, and as the quantity gets big, traditional manufacturing does better. So for the three important categories of plastics, metals, and ceramics, where is that crossover now? And where do you see that crossover moving in 5 years to higher quantities?
We have, it's hard to do that on anything but a part-by-part basis, because you can take an air duct extension, which is this big, and you're going to have a break-even quantity of like 5 or something like that, right? Or, transition quantity 5, when the tool is really simple, the part's very small and whatnot. If you take that and make it 4 feet longer, that is typically going to move into the dozens. So that's typically where we are for the polymers and whatnot. For metals, you might want to ask the engine people a little more on that, because they've done more work in it. But for us, from our perspective now, the primary hurdle is going to be all the testing required to get those, and all the process development that's going to have to be done prior to that, in addition to testing, to get those materials to a place of confidence. So the answer for that, from our perspective, is there is no cutoff point right now for metals, because it's really something we haven't invested in heavily. Again, the engine manufacturer is going to be a little bit more further along in that place. But for polymer parts, in the dozens typically per dozen, 2 dozen, something like that parts per aircraft. Depends on the rate of the program too.
I think that's going to have to be the last one to stay on schedule. So apologies, but
Yep.
You'll get a chance in the panel discussion. So thank you very much, Brent.